Humanity's dream of space travel became reality with the Space Shuttle. The Space Shuttle symbolized human ambition and reshaped space exploration. The Space Shuttle aimed to make space travel affordable and reusable. NASA's Space Shuttle fleet marked a new era in spaceflight. The Space Shuttle program spanned 3 decades of groundbreaking missions. The orbiter was a reusable spaceplane, blending spacecraft and aircraft features. The external fuel tank powered the Space Shuttle's main engines. Solid rocket boosters provided the initial thrust for Space Shuttle launches. The thermal protection system shielded the orbiter during re-entry. The shuttle's main engines propelled it into orbit with remarkable efficiency. Section 3, Precision and Control, guiding the spaceplane. Unlike conventional rockets, which were essentially ballistic projectiles, the Space Shuttle had the ability to maneuver in space and glide back to Earth for a runway landing. This remarkable capability was made possible by the orbiter's sophisticated flight control system, a complex network of sensors, actuators, and computers that allowed the crew to precisely control the vehicle's orientation and trajectory. The orbiter's flight control system relied on a combination of aerodynamic surfaces, reaction control system thrusters, and the Space Shuttle's main engines. The aerodynamic surfaces, including the wings, tail, and elevons, provided lift and maneuverability during atmospheric flight. The RCS thrusters, strategically positioned around the orbiter, fired small bursts of hypergolic propellant to control the vehicle's orientation in the pitch, yaw, and roll axes. The Space Shuttle's main engines, in addition to providing thrust for launch and orbit insertion, were also used for orbital maneuvers and deorbit burns. By precisely controlling the thrust and gimbal of the main engines, the crew could adjust the orbiter's velocity and trajectory, allowing it to rendezvous with satellites, dock with the International Space Station, and initiate its descent back to Earth. Section 1, A Blaze of Glory launch and ascent. The culmination of years of planning, engineering, and preparation, a Space Shuttle launch was an awe-inspiring spectacle, a testament to human ambition and technological prowess. The countdown, a slow, deliberate march towards zero, built anticipation to a fever pitch. Then, with a deafening roar that shook the ground and rattled the soul, the Space Shuttle roared to life, unleashing a torrent of fire and smoke that illuminated the Florida sky. The 2 solid rocket boosters, ignited first, provided the initial thrust, their combined power propelling the massive vehicle skyward. The ground trembled, the air crackled with energy, and a plume of white-hot exhaust billowed out from the launch pad, dwarfing everything in its wake. The Space Shuttle, a symbol of human ingenuity, was on its way, embarking on a daring journey to the final frontier. As the Space Shuttle ascended through the atmosphere, the roar of the engines reverberated through the air, a visceral reminder of the immense power unleashed. Inside the crew compartment, strapped into their seats, the astronauts were subjected to intense G-forces, their bodies pressed back against their restraints as the vehicle accelerated skyward. The Earth receded below, shrinking in size until it was just a distant sphere, a pale blue dot against the blackness of space. Section 2, Weightless Wonders orbit operations. Upon reaching an altitude of about 60 miles, the Space Shuttle's main engines cut off, and the solid rocket boosters, their fuel depleted, separated from the external tank. The boosters, now falling back to Earth, would eventually parachute into the ocean for recovery and reuse. Meanwhile, the Space Shuttle, still attached to the external tank, continued its ascent, its main engines reigniting to propel it into orbit. With a final burst of speed, the space shuttle achieved orbital velocity, approximately 17,500 miles per hour. At this speed, the vehicle was essentially in a constant state of freefall, circling the Earth every 90 minutes. Inside the orbiter, the astronauts experienced the peculiar sensation of weightlessness, their bodies floating freely as if gravity had been suspended. Once in orbit, the crew set about their mission, which could range from deploying satellites to conducting scientific experiments to assembling and maintaining the International Space Station. The orbiter's payload bay, now exposed to the vacuum of space, became a hive of activity, with astronauts conducting spacewalks to deploy payloads, repair satellites, or install components on the space station. Section 3. A fiery return, re-entry and landing. After completing their mission, which could last for days or even weeks, the astronauts prepared for the space shuttle's return to Earth. This final phase of the mission, while less dramatic than launch, was arguably more perilous. The space shuttle, no longer protected by the Earth's atmosphere, would plunge back into the planet's gaseous envelope at hypersonic speeds, generating intense heat due to friction. To survive this fiery re-entry, the orbiter relied on its remarkable thermal protection system, a shield of heat-resistant tiles that covered its underside and leading edges. As the space shuttle descended through the atmosphere, the tiles glowed red-hot, absorbing the intense heat and protecting the vehicle's aluminum structure from melting. As the space shuttle slowed down, the intense heat subsided, and the orbiter transitioned from a spacecraft back into a glider. With no engines to power its descent, the orbiter relied on its aerodynamic shape and the skillful piloting of the crew to glide to a safe landing on a runway. The landing, a testament to the space shuttle's unique design, marked the end of another successful mission, a testament to human ingenuity and our insatiable thirst for exploration. A symphony of engineering, the shuttle's manufacturing process. Building a space shuttle was an intricate symphony of craftsmanship, technology, and human endeavor. Components were manufactured by a network of contractors across the United States. The orbiter was built by Rockwell International in Palmdale, California. Skilled technicians meticulously pieced together the orbiter's structure and thermal protection tiles. The external fuel tank was assembled at the Michoud Assembly Facility in New Orleans. The solid rocket boosters were manufactured by Thiokol in Utah. Section 2. Forged in fire materials of an orbital behemoth. The extreme conditions encountered by the space shuttle demanded materials with exceptional properties. Engineers turned to advanced materials for strength, weight, and heat resistance. Aluminum alloys formed the backbone of the space shuttle's structure. Titanium alloys were used in high-temperature areas like the nose cone and wing edges. The Thermal Protection System, or TPS, protected the vehicle from re-entry heat. The main engines, made of Inconel, withstood extreme temperatures and pressures. Section 3. From parts to pinnacle system integration at the vehicle assembly building. Once the space shuttle's major components were transported to the Kennedy Space Center, the daunting task of assembling them into a flight-ready vehicle began. This critical phase took place inside the iconic Vehicle Assembly Building, or VAB. The VAB, one of the largest buildings in the world by volume, served as the primary assembly and integration facility for the Space Shuttle program. The orbiter, external tank, and solid rocket boosters were carefully lifted and mated together. This complex process required meticulous precision and coordination. Once fully assembled, the Space Shuttle underwent rigorous tests. After passing all tests, it was transported to Launch Complex 39, marking the final stage of its journey from factory floor to launch pad. Cosmic couriers, deploying satellites and probes. The Space Shuttle played a pivotal role in expanding humanity's presence in space. One of its primary missions was deploying satellites, relaying communications, collecting data, and providing navigation. From communication satellites to weather satellites, the Space Shuttle launched technological marvels indispensable to modern life. Astronauts, using the shuttle's robotic arm, would carefully lift and release satellites into space. The Space Shuttle also deployed interplanetary probes, revolutionizing our understanding of the solar system. The shuttle's role extended beyond deploying satellites and probes. It also served as a platform for retrieving and repairing satellites already in orbit. Eyes on the universe, scientific research and discovery. Beyond its role as a transportation system, the Space Shuttle was also a remarkable scientific platform, enabling a wide range of experiments and observations in the unique environment of space. The shuttle's microgravity environment, where the effects of gravity are significantly reduced, provided an unprecedented opportunity to study fundamental physical phenomena and biological processes in ways not possible on Earth. Scientists from around the world competed for the opportunity to fly experiments aboard the Space Shuttle, eager to take advantage of this unique research environment. Experiments ranged from studying the behavior of fluids in microgravity to investigating the effects of spaceflight on the human body. The data collected during these missions provided invaluable insights into a wide range of scientific disciplines, advancing our understanding of physics, chemistry, biology, and medicine. The Space Shuttle also carried specialized instruments for astronomical observations, taking advantage of its position above Earth's atmosphere, which blocks many wavelengths of light. These instruments, including telescopes and spectrographs, allowed astronomers to observe the universe in greater detail and across a wider range of wavelengths than possible from ground-based observatories. The shuttle's contribution to astronomy extended beyond its own observations. It played a pivotal role in deploying and servicing the Hubble Space Telescope, one of the most important scientific instruments ever built. Hubble, orbiting high above Earth's distorting atmosphere, has captured breathtaking images of the cosmos, revolutionizing our understanding of the universe and inspiring generations with its awe-inspiring views of distant galaxies, nebulae, and star-forming regions. The price of progress, challenges and risks. The Space Shuttle program, a testament to human ingenuity, faced significant challenges and risks. Spaceflight inherently carries risks, and the shuttle program experienced its share of tragedy. These painful experiences provided invaluable lessons for future space exploration. The tragic losses of Challenger and Columbia underscored the inherent risks of spaceflight. A legacy of innovation, shaping the future of space exploration. Despite challenges, the Space Shuttle program left an indelible mark on space exploration. It demonstrated reusable spacecraft viability, paving the way for commercial space ventures. Companies like SpaceX and Blue Origin are driving down the cost of spaceflight. The Space Shuttle advanced our understanding of space and our place within it. Its deployment of the Hubble Space Telescope revolutionized our understanding of the universe. The program inspired generations with its daring missions and message of human ingenuity. The sight of the shuttle launching captivated imaginations and ignited dreams of space travel. As we plan missions to Mars and beyond, the lessons from the Space Shuttle will guide us.
Like and subscribe to start your journey today.